In this video, we want to find the inverse of a 3 by 3 matrix. So let's go back to the A matrix that we used in a previous video, which was 3 by 3. And the first row elements in that matrix were 1, 0, 2. The second row elements were 0, 1, 1. And the third row elements were -1, 2, and 3. And we showed in the earlier video that the determinant of this A matrix was equal to 3, which was not equal to 0, and therefore we know that the inverse of that A matrix does exist. And how do we find it? Recall that the formula for the inverse of the A matrix was 1 over the determinant of A times the adjoint of the A matrix, which was just the transpose of the cofactor matrix. So now we need to find the cofactor matrix of the A matrix. And the way we do that is as follows. Remember that the way we find the cofactor matrix is that we simply replace every element of the A matrix with its cofactor. So if the A matrix is 3 by 3, the cofactor matrix of the A matrix will also be 3 by 3. But in this case, let's illustrate it step by step. So recall that the elements of the A matrix can be thought of in general as A11, A12, A13, A21, A22, and so on. So let's go back to the first element, A11, which in this case is 1, and find the cofactor of that element. Well, the cofactor of element A11 is the minor of element A11, which is the subdeterminant of the A matrix after we delete the row and column containing that element A11. So we're going to get the determinant with the elements 1, 1, 2, and 3. Now we need to attach a sign to that minor to get the cofactor of element A11. Well, let's see. If we look at element A11, 1 plus 1 is 2, which is even. So we're going to attach a plus sign to that minor of element A11 to get the cofactor of element A11. How do we find the cofactor of element A12? We need the minor of element A12, which is going to be a subdeterminant after we delete the row and column containing that element. So the subdeterminant will contain the elements 0, 1, -1, and 3. How do we find the cofactor of element A12? 1 plus 2 is 3, which is odd. So we attach a negative sign to that minor, and we get the cofactor of element A12. Finally, the cofactor of element A13 is the minor of element A13, which is the subdeterminant containing the elements 0, 1, -1, and 2. And since we're looking at the cofactor of element A13, 1 plus 3 is 4, which is even, so we attach a positive sign to that minor. And we need to repeat this procedure for the remaining elements of the A matrix to get the remaining elements of the cofactor matrix. After we do that, you should be able to show that the final cofactor matrix contains the elements in the first row, 1, -1, and 1. In the second row, 4, 5, and -2. And in the third row, we have the elements -2, -1, and 1. Now we need to find the transpose of the cofactor matrix, which is also known as the adjoint of the A matrix. So how do we find the transpose of the cofactor matrix? We go back to the cofactor matrix. We take its first row, and it becomes the first column of the transpose of the cofactor matrix. We take the second row of the cofactor matrix and make it the second column of the transpose of the cofactor matrix. And we do the same thing for the third row of the cofactor matrix, making it the third column of the transpose of the cofactor matrix. Now we can simply write out what the inverse of A, or what the inverse matrix of our A matrix is. It's 1 over the determinant of A times the adjoint of A, whose elements in the first row are 1, 4, minus 2. In the second row, minus 1, 5, minus 1. And in the third row, 1, minus 2, 1. And if we multiply our matrix by the scalar 1/3, we get the following result. First row, 1/3, followed by 4/3, followed by minus 2/3. The elements in the second row become minus 1/3, 5/3, and minus 1/3. And the elements in the third row become 1/3, minus 2/3, and 1/3. And again, you should check to see if this is the inverse of A by multiplying the matrix A by the inverse of A and seeing if you recover a 3 by 3 identity matrix.